Students, in this video we are going to learn about elimination reaction. So this is the NCERT line by line series. So previous videos, if you have not watched, you can watch those videos. All the important concepts I have written here, and also I have made use of stick notes. So you can see here the stick notes are here and all the important concepts are written here. You can go through the other videos as well. So here revision will be very easy for you. So within few minutes you will be able to revise the entire concepts. So let us start with elimination reaction. So what is elimination reaction is, from one carbon halogen and from the adjacent carbon if hydrogen is removed, it results in the formation of a double bond, which is called as elimination reaction. So usually here the halogen will be attached to a carbon, and that carbon is called as alpha carbon. The adjacent carbon is called as beta carbon, and in the beta carbon hydrogen atom should be present. So that hydrogen atom and this halogen both will be removed. As a result, a double bond will be formed. So here you can see, when a halogen with beta hydrogen atom is heated with alcoholic solution of potassium hydroxide, that is alcoholic KOH you are using. So when you are using alcoholic KOH, elimination of hydrogen from the beta position and halogen from the alpha position will take place, which is called as elimination reaction. It is also called as beta elimination because hydrogen atom is removed from beta carbon. See here, since beta hydrogen atom is involved in elimination, it is often called as beta elimination. If there is a possibility of formation of more than one alkene due to the availability of more than one beta hydrogen atom, so usually one alkene will be formed as the major product. So suppose if more than one product is formed, one will be the major product, and that product will be formed according to Seitzeff rule. So before reading this Seitzeff rule, we will see this example. So 2-bromopentane. So at the second carbon you can see bromine atom is present. So here we said that from the beta carbon hydrogen you have to remove. So this is the alpha carbon. Halogen will be attached to alpha carbon. So this will be beta carbon, and here this will be beta carbon. There are two beta carbon atoms. So here this hydrogen and this halogen can be removed, and a double bond will be formed between second and third carbon atom. And other possibility is, this beta carbon hydrogen and halogen can be removed. As a result, double bond can be formed between first and second carbon atom. So now two alkenes are formed, pent 2-ene and pent 1-ene. So now one is major, pent 2-ene is major and pent 1-ene is minor. So this is according to Seitzeff rule. So what Seitzeff rule says is, after the formation of the alkene, you should see more number of alkyl groups if it is present, that will be the major product. So here this is the double bonded carbon atom. How many alkyl groups are present? One alkyl group and second alkyl group. So there are two alkyl group attached to the carbon-carbon double bond. And here in this product you see carbon-carbon double bond, and there is only one alkyl group attached. So here there are more number of alkyl groups, therefore this will be the major product. So now we will go through the Seitzeff rule. So what Seitzeff rule says is, in dehydrohalogenation reaction, the preferred product is that alkene which has the greater number of alkyl groups attached to the doubly bonded carbon atom. So here the doubly bonded carbon atom should have greater number of alkyl group. So here there are two and here there is only one. So this will be the major product according to Seitzeff rule. So this reaction is also called as dehydrohalogenation. So dehydro meaning is we are removing hydrogen as well as halogen. Therefore it is called as dehydrohalogenation reaction. So now we have seen about substitution reaction. So haloalkanes can undergo substitution reaction as well as elimination reaction. So when they will undergo elimination and substitution reaction depends upon so many factors. That is, depends upon the type of nucleophile, the type of base, and also the reaction conditions. So here they have given in the textbook, it depends upon, you can see, make a note of this. It depends upon nature of the alkyl halide. So this is the first reason. Second is strength. And third is size of the base or nucleophile. And then reaction conditions. So it depends on all these conditions. So suppose if the nucleophile is bulky, means if it is bigger, so whether substitution reaction will take place or elimination reaction take place. So you can see elimination reaction will take place if the nucleophile is bulky in nature. So you can see this picture. This is the alkyl halide and here this is the nucleophile. So this you can see it is a bulky nucleophile which is present, and this is the carbon atom. And so this bulky nucleophile, it is difficult for it to travel here and attack the carbon. Instead of that, it will remove the hydrogen atom. So this will be acting as a base instead of nucleophile. Therefore, elimination reaction will take place. And if it is a primary alkyl halide, then SN2 reaction will be preferred. So that we have already seen. And if it is secondary alkyl halide, it can be SN2 reaction or it can be elimination reaction. So it can be any one. It depends upon the type of base or the type of the nucleophile. If it is tertiary alkyl halide, it can be SN1 reaction or it can be elimination reaction. So it depends upon the stability of carbocation or the stability of alkene which is formed. So depending on that, you have to choose whether it undergoes elimination reaction or nucleophilic substitution reaction. So you can see in this picture. So here substitution reaction takes place because this is the nucleophile which is smaller. It is not bulky. Therefore, it can go and attack the carbon atom. Therefore, and Br will leave as Br minus. Therefore, here substitution reaction is taking place. Next is reaction with the metals. So here mainly we are going to study about Grignard reagent. So what is Grignard reagent? Alkyl magnesium halide, RMgX. General formula you should remember, RMgX. So the metal which is used here is magnesium. Alkyl magnesium halide is called as Grignard reagent. These reagents are obtained by reaction of haloalkane with magnesium metal in dry ether. So this is very important. We are using dry ether condition, means water content should be absent. So why the water content should not be there? If water content is present, this will be converted back to hydrocarbon. So this can be asked, the reason why it should be under dry condition. If moisture is present, what will happen? If moisture is present, this will be converted into hydrocarbon. Therefore, we are using dry ether. So here first we are taking alkyl bromide. We are treating with magnesium in the presence of dry ether. You can see Grignard reagent is obtained. So mainly here what you should see is carbon metal bond will be formed. Here you can see carbon and magnesium bond will be formed in the Grignard reagent. In the Grignard reagent, the carbon magnesium bond is covalent but highly polar, with carbon pulling electron from electropositive magnesium. The magnesium halogen bond is essentially ionic. So this question can appear in the examination. So see here, this is carbon and this is magnesium. So between carbon and magnesium, the bond which is present is called as covalent bond. So it is covalent bond, still it is polar in nature. It is highly polar in nature. So carbon will pull this electron towards itself. As a result, it will be getting partial negative sign and magnesium will be getting partial positive sign. And the bond which is present between magnesium and halogen is ionic in nature. So because of which you can see halogen will be having partial negative sign and magnesium will be having partial positive sign. So there are two types of bonds present which you have to make a note. So between carbon and magnesium it is covalent bond. Between magnesium and halogen it is ionic bond which is present. So here you can see in the textbook. Grignard reagents are highly reactive in nature and react with any source of proton to give hydrocarbon. So any source which gives proton, that is H plus ion, then it will be converted back into hydrocarbon. So even water, alcohol, amines are sufficiently acidic to convert them to hydrocarbons. So here what they have given is Grignard reagent. Even if a proton source is present, it will be converted into hydrocarbon. So here what the source what is given is water, alcohol and amines. Remember, so in one of the NEET examination it was given water. When Grignard reagent is treated with water, what is the product obtained? So you should know if it is treated with water or it can be alcohol or it can be amine, the product will be hydrocarbon. So it will break here and hydrogen will be attached to R. So you will be getting hydrocarbon. So it is necessary to avoid even traces of moisture from Grignard reagent. So that is why the reaction is carried out in dry ether. So that is why we are carrying out in dry ether. So the reason is even if moisture is present, Grignard reagent will be converted into hydrocarbon. So next is Woods reaction. So Woods reaction is nothing but you are taking alkyl halide and you are treating with sodium in the presence of dry ether. So here you are taking 2 alkyl halide. So take Rx and then Rx. So here Rx and Rx we will take. So the halogen and sodium will be removed and halogen, just a minute, I'll write down the reaction. So Rx, you are treating with sodium and then you are treating again with one more alkyl halide, Rx. So this will be removed and you will be getting R. So this is called as Woods reaction. So next we will see reaction of haloarenes. So this is very important about haloarenes, how they are going to react. So nucleophilic substitution reaction. So usually haloarenes will not show nucleophilic substitution reaction. For that 4 reasons are given here. So we will see all those 4 reasons. One is resonance effect. So in the resonance effect what will happen is you can see the electrons which are present on the chlorine is involved in resonance here with the benzene ring. So it shifts like this, you can see. These are the resonance structures. So here you can see there is a carbon, there is a double bond between carbon and chlorine. Because of resonance, you can see a partial double bond character exists between carbon and chlorine. Therefore, breaking these bonds become very, very difficult. Breaking this bond, that is carbon and chlorine bond, becomes very difficult. Therefore, substitution reaction is difficult here. You can see carbon chlorine bond acquires a partial double bond character due to resonance. Therefore, cleavage meaning is breaking of this bond becomes very difficult. Second is difference in hybridization of carbon atom in CX bond. So here you can see this is haloarene and this is haloalkane. So here this carbon atom is sp2 hybridized. Halogen is attached to sp2 hybridized carbon atom, whereas here in haloalkane halogen is attached to carbon and this carbon is sp3 hybridized. So here since it is sp2 hybridized, the carbon is sp2 hybridized, S character is 33%, whereas here the S character is 25%. So more the S character, more will be electronegative in nature. So the carbon atom which is present here will be more electronegative when compared to this carbon atom. So as a result, what you can see is this carbon atom will pull electron close to itself. As a result, you can see the bond length between carbon and chlorine will be less. So that is 169 picometer, whereas in haloalkane, you can see the carbon chlorine bond length is bigger, which is 177 picometer. So it has a longer bond. So if it is short bond, it is difficult to break this bond. If it is longer, you can easily break this bond. Therefore, in haloarene, again it is difficult to break this bond because the carbon atom is sp2 hybridized, and because of which the bond length will be shorter. So this is the second reason. Third reason is instability of phenyl cation. So phenyl cation meaning is, suppose if this is the benzene ring to which halogen is attached like this. So when you remove this halogen atom on the benzene ring, there is a carbocation, there is a positive sign which is formed. So now this is called as phenyl cation. So phenyl cation is highly unstable in nature. So this is a positive sign on the carbon atom. So this is called as phenyl. This is called as phenyl cation. Phenyl cation is highly unstable in nature because it is not stabilized. So this is one reason why nucleophilic substitution reaction will take place. Particularly, you can see this SN1 mechanism is completely ruled out. Why SN1 mechanism is completely ruled out? Because SN1 mechanism proceeds through carbocation formation. So here carbocation formation results in instability. It is unstable in nature. Therefore, SN1 mechanism is ruled out. And fourth one is very simple, because of possible repulsion. Suppose if a nucleophile approaches here. So here so here suppose if this is the haloarene. So you know that inside the benzene ring there are double bonds. So benzene ring is electron rich. Nucleophile is also electron rich. So if both are electron rich, you know that they will repel each other instead of attraction. So therefore nucleophilic substitution becomes very difficult. So these are the four possible reasons why haloarene will not show nucleophilic substitution reaction. It is very difficult to show nucleophilic substitution reaction because of four reasons. One is resonance effect. Because of resonance effect, a double bond, a partial double bond character will exist between carbon and chlorine. Therefore, it becomes difficult to break this bond. Second is difference in hybridization of carbon atom. So in haloarene, the carbon atom is sp2 hybridized. In haloalkane, it is sp3 hybridized, because of which the carbon halogen bond length becomes shorter. Therefore, it is difficult to break the bond. Third is instability of phenyl cation, and fourth is because benzene ring is electron rich. So nucleophile is also electron rich. So therefore, they will repel each other. So till now what we have seen is it is difficult for the haloarenes to show nucleophilic substitution reaction, but under drastic condition they are going to show nucleophilic substitution reaction. So these are the examples we are going to study for that. That is replacement by hydroxyl group. So here take chlorobenzene. So here you can see the drastic conditions here. Temperature is very high, 623 Kelvin you have to maintain, and pressure you have to maintain 300 atmosphere. So in the presence of a base and H plus ion. So when you are treating with the base NaOH, so this will be replaced by ONA. So here remove this Cl and write here ONA, and then this should be acidified with H plus ion. When it is acidified, this will be converted into OH. So here you will be getting the product. The presence of electron withdrawing group like NO2 group at ortho and para position increases the reactivity of haloarenes. So here you can see NO2. NO2 is a electron withdrawing group. So if it is electron withdrawing, it reduces the electron density now. So when it is reducing the electron density, then the nucleophile can approach this. Therefore, here you can see the temperature here it was 623. So when an electron withdrawing group is present, temperature see here it is reducing to 443 Kelvin, 443 Kelvin. So you can replace chlorine with OH group. And if two NO2 groups are present, electron withdrawing groups are present, so it will reduce the electron density of the benzene ring further. So because of which you can make a note of this temperature. Still at lower temperature you can see chlorine group will be replaced by OH. And here you see when 3 electron withdrawing groups are present, so it reduces the electron density on the benzene ring. So even slightly if you warm it, so you can see here chlorine will be replaced by OH group. So here what you have to learn is a temperature. So at higher temperature, so you can see here the chloro group will be replaced by OH. If one nitro group is present, so temperature you have to make a note, 443 Kelvin, you can replace chlorine with OH group. And then 368 Kelvin, and then if 3 electron withdrawing groups are present, even if you slightly warm, you can convert Cl to OH group. So we have seen that electron withdrawing group should be present only at the ortho and para position. So if it is present at the meta position, it doesn't have any effect. So the reason is given here clearly, you can see. See here, if nitro group is present at the para position, these are the resonance structures. So in the resonance structures, you can see negative sign is present at the ortho position. Here it is present at the para position. Here the negative sign is present at the para position. So when the negative sign is present at the para position, nitro group is also present at the para position. So this negative sign will be in resonance. So negative sign, single bond, double bond. So they will be in resonance. So they will stabilize it. Therefore, at the para position, if it is present, it will reduce the electron density. So this electron density will be pulled by the nitrogen. So it also undergoes resonance. If it is present at the ortho position, see here, nitro group is present at the ortho position. So even then resonance structures you observe, negative sign is present at the ortho position, para position and ortho position. So when negative sign is present at the ortho position, so this will be in resonance with the nitro group, because negative sign, single bond, negative sign, single bond and then double bond. So they will be in resonance. Therefore electron density they are going to reduce. So therefore even at the ortho position it is present, it will reduce the electron density. Whereas if it is present at the meta position, so observe this resonance structures. Negative sign is present at the ortho position, at the para position and at the ortho position. So at the meta position there is no negative sign at all. So therefore nitrogen cannot take that negative sign, or it cannot reduce the electron density of the benzene ring. Therefore nitro group present at the meta position doesn't have any effect. So that is what is given here. Clear explanation is given. Why nitro group present at the meta position doesn't have any effect? It is because in the resonance you can see negative sign is not present at the meta position. Therefore they cannot reduce the electron density. Whereas in ortho and para position, negative sign is present at the ortho position and para position. Therefore they can reduce the electron density. So go through this. Next is electrophilic substitution reaction. So haloarenes will not undergo nucleophilic substitution reaction, but they are undergoing electrophilic substitution reaction. So here you can see such as halogenation, nitration, sulfonation and Friedel-Crafts reaction. Halogen atom, beside being slightly deactivating, is ortho-para directing. So here you can see chlorobenzene or halogen is present. So halogen usually it will show minus I effect. So here I have written, you can see here, halogen they are deactivating group because they show minus I effect, but they also show plus M effect. By plus M effect they will show ortho para, they are showing ortho para directing groups. So here you can see due to resonance the electron density increases more at the ortho para positions. So here because of this plus M effect, you can see negative sign is present at the ortho position and as well as the para position. Therefore they will show ortho para directing groups. Further, the halogen atom, because of its minus I effect, has some tendency to withdraw the electron from the benzene ring. As a result, the ring gets somewhat deactivated as compared to benzene. So now halogens are showing minus I effect. So therefore they will pull this electron, the electron which is present here will be pulled towards the halogen. So they are decreasing the electron on this carbon. So therefore they are deactivating group. Remember that always in halogen, since they are showing two effects, minus I effect they are showing as well as they are showing plus M effect. But what is dominant in halogen is minus M effect is dominating in halogens. So now we will see first halogenation. So in halogenation, remember that here you are treating with chlorine in the presence of anhydrous ferric chloride. So you will be getting ortho product as well as para product, and para product is found to be always major. Here which is the electrophile formed? This is electrophilic substitution reaction. So the electrophile which is formed here is Cl plus. So from here, hydrogen which is present here, remove this hydrogen and replace with H plus. So Cl will come and attack here. So therefore you are getting a chloro group here. So the electrophile which is formed here is Cl plus. And in nitration we are going to use concentrated sulfuric acid and nitric acid. So the halogen which will be produced here is NO2 plus. So here you should know the electrophile which is produced. So in nitration, the electrophile which is produced here is NO2 plus. So you will be getting ortho product and para product. The major one will be the para product. And then sulfonation. Sulfonation is treating with concentrated sulfuric acid. So here the electrophile which is formed here is SO3H plus. So this is the electrophile which is produced. So at the ortho position, one product you will get and para product you will get. The major one will be always para product. So you can remember. Next is Friedel-Crafts reaction. So Friedel-Crafts reaction, you have two types of reagents. That is alkyl halide and acyl halide. Acyl halide is CH3COCl. So this is acyl halide. And here you have to use anhydrous aluminum chloride. So here what is the electrophile which is produced? Here the electrophile produced is CH3 plus methyl cation will be formed. So CH3 plus will be attached to the ortho position or at the para position. Always remember para will be the major product. And here acyl chloride. So here which is the electrophile which is produced? CH3 C double bond O plus. This is the electrophile which is produced. So at the ortho position it will get attached and then para position. So the major will be the para product. So this is Friedel-Crafts acylation and this is Friedel-Crafts alkylation reaction. There are two types of Friedel-Crafts reaction, alkylation and acylation. So if you want to study the mechanism, so you can go through the playlist. I have taught even the mechanism how it happens. So now we will solve the example sums. Although chlorine is an electron withdrawing group, yet it is ortho-para directing in electrophilic aromatic substitution reaction. Why? So you know that it is deactivating group. It shows minus I effect. So because of which you can see that here it is taking electron towards itself because of minus I effect. So the positive sign which is formed here on the carbon atom, so it is pulling the electron towards itself and it is destabilizing. So inductive effect will destabilize the intermediate carbocation which is formed. So here carbocation is formed. So that carbocation is destabilized by chlorine atom by pulling the electron towards itself by minus I effect. And here because of resonance, you can see here because of resonance it will be showing, it will be stabilizing this plus I effect. These electrons are moving here, so it is stabilizing this carbon atom. So resonance effect stabilizes the intermediate carbocation which is formed. The inductive effect is stronger than resonance and causes net electron withdrawal and thus causes net deactivation. So deactivation will be greater. Why? Because minus I effect is dominant over plus M effect in case of halogens. So this point is very important. Make a note of it. So next we have Woods-Fittig reaction. So here in Woods-Fittig reaction, what you will take is, you will be taking aryl halide and then alkyl halide in the presence of sodium dry ether. So you will be getting this alkyl group will get attached to the aryl group. So this is the product which is formed in the Woods-Fittig reaction. So just now we have seen about Woods reaction. In Woods reaction, you will be taking 2 alkyl halide. Here aryl halide and alkyl halide. In Fittig reaction, you will be taking 2 aryl halide. So 2 aryl halide when you are treating with sodium in dry ether. So here, so this is 1 aryl halide. You are treating with sodium, and then this is another aryl halide. So here this will be eliminated. 2 NaX will be eliminated and you will be getting the product like this. So this is the product which is obtained. Now we will solve in text question. Which alkyl halide from the following pairs would you expect to react more rapidly by SN2 mechanism? So we will see which one will undergo the rate of SN2 mechanism will be shown higher. So this is first one and this is second one. So you know that in SN2 mechanism, the rate of primary alkyl halide will be greater than secondary and then tertiary. So now we will see here halogen is attached to this carbon which is primary carbon, and here halogen is attached to secondary carbon. So primary carbon, the rate will be more. So you have to write, this is the one which shows the rate will be higher. And in this two we will see, so halogen is attached to secondary carbon and here halogen is attached to tertiary carbon. So secondary carbon, the rate will be greater. So the answer is this one. And here halogen is attached to primary. Here also halogen is attached to primary. So this is very important. So when it is attached to primary carbon, so next what we have to check is about steric hindrance. So if here you can see there is a branch. So if the branch is closer to halogen, so here you can see branch is closer to the halogen. So steric hindrance will be more. If steric hindrance will be more, the rate will be less. So here the rate is less. Therefore the rate will be more in this case. Next, in the following pairs of halogen compound, which compound undergoes faster SN1 reaction? So for SN1 reaction, the rate of reaction will be greater for tertiary and then secondary and then primary. So here we will compare these two. So here halogen is attached to tertiary and here halogen is attached to secondary. So the rate will be greater in tertiary. And here we will compare these two. Halogen is attached to secondary, halogen is attached to primary. So therefore the rate will be greater in secondary. So now identify A, B, C, D, E, R and R dash in the following reaction. So we'll do this now. So we are treating this reactant with magnesium in dry ether. So what is the product you are getting? So magnesium means, remember this is a Grignard reagent, magnesium with dry ether. So Grignard reagent, so what the product you will get is, you will be getting, so here carbon magnesium bond will be formed, MgBr. So this is the product obtained. So always remember between carbon, so this is carbon and this is halogen. When you are treating with magnesium, between carbon and magnesium bond will be formed. So here you can see carbon magnesium bond is formed. When you are treating with water, so I told you that it can be water or it can be alcohol or it can be amine. So they will donate proton, because of which here you can see hydrocarbon will be obtained. So this is going to break and here H will attach. So the product will be, so B will be this. So B is this. Next. So RBr, again you are treating with magnesium in dry ether. So again it is a Grignard reagent, you will be getting C. And here this C, when you are treating with D2O. So instead of water, here deuterium oxide is given, D2O. So you are getting this product. So here D is attached to this carbon. So meaning is See here, we are removing this MgBr and we are attaching hydrogen here. So if D is attached to this carbon, meaning is here MgBr was present. So here you can write. So C will be this CH3, CH3, and here it will be MgBr. So here what is R then? So R will be, so if you remove this MgBr, so see here RBr, you are treating with magnesium. So you know that magnesium will form bond between carbon and magnesium. So this you have to remove. So R will be, so this will be CH3, CH3Br. So now once again you go through this. CH3Br, when you're treating with magnesium in dry ether, what happens is between carbon and magnesium a bond will be formed here. Therefore you will be getting CHMgBr. When you're treating with the D2O, so this will be removed. In that place deuterium will be attached. So C will be this. So next we will see R-X when you are treating with sodium in dry ether. So sodium in dry ether, meaning it is Woods reaction. So always remember sodium in dry ether will be Woods reaction. So here this is the product formed. So meaning is this, break this into two. So this is one alkyl group and this is second alkyl group. So here R dash would have been this CH3, and X. So here two molecules will combine together. So same two molecules will combine together and this Woods product you will get. And this side, this when you are treating with magnesium, so this is Grignard reagent. When you are treating with magnesium, what will happen? Between this carbon and magnesium a bond will be formed. So it will be CH3 MgX. And when you're treating with water, so this one you're treating with water. So when you're treating with water, so here this will give CH3 and H. So you're removing this MgX and you're placing hydrogen. So this is E and this is D and this is R-X. So this completes haloalkanes and haloarenes. So students, go through it. It's very important. So go through NCERT at least 5 to 6 times you will have to revise. Only then you will get confidence in NEET examination to solve any kinds of questions. So here you can see in this chapter all the important points I have written at the corner and also stick notes I have written. So revise this several times so that the concepts becomes clear to you and you can attempt all the questions. So all the very best students. I'll meet you in the next video.